Oops.
1 minute to 9 o'clock. So we will start after probably 2 or 3 minutes later.
Mm-hmm.
Okay, I think most students are here, no matter in the classroom or on Zoom. So I believe we may start. Professor Toshiaki Ojizawa. Sorry,
Yes.
I'm not good at Japanese.
Yeah.
Well, from Taiwan, from Tokyo Tech, and he's going to present the characteristics of polymers. Let's welcome Professor Toshiaki.
Okay, thank you very much. So, good morning, everybody. So my name is Toshiaki Ogizawa. I belong to the Department of Materials Science and Engineering. Can you hear me? No problem? Okay. Can you hear me? Okay. So at first, yeah, I give a lesson first 1 hour. After that, I exchange it to Professor Kuboyama's. Yeah, afternoon, I will go to the abroad. So maybe I change Professor Kuboyama's. So anyway, let's start my lecture class. Okay. So my major is polymer science, almost polymer physics. So today, oops. Yeah, at first, what molecules are plastics and rubbers made of? So maybe you know that the covalent bond with molecular hydrogens. So this is a very strong bond. Okay. So, but this one is a methane. Methane is a CH4. So hydrogen is located at the vertex of the tetrahedrons. So in this case, this angle, this one is a regular tetrahedron angle. This is almost constant, almost from 108 to 110. So almost fixed one. So that's the structure of methanes. So this is the 3D structure as well. So hydrogen located as a vertex of the tetrahedron, this one. So we change 2H to carbon, this one. So maybe carbon backbones connected one. In this case, this one become polymers. Okay, so that's a very simple structure, this one. So what is a plastics? So a general term, if it's this one is a package food container in convenience stores. So maybe that's very popular for use. So anyway, a general term of high molecular weight materials exhibit plasticity under heat or pressure and can be processed and molded into the desired shape. In most cases, it referred to thermoplastic resin. But sometimes we call it thermoplastic polymers. Okay, so a polymer with a glass transition temperature Tg or crystal melting point Tm above room temperature and almost no fluidity at room temperatures. So at room temperature, almost solid. So usually solid become that materials. Okay. So what is rubbers? Yeah, for example, tire. That one is from that rubbers. Rubber is a general term for the substance that deforms greatly when a force is applied, but returns to its original shape as soon as the force is removed. Chain-like polymers with chemical and physical cross-linking and Tg below room temperatures. So that means that, in brief, both are chain polymers that solidify at temperature above or below room temperatures. So, yeah, rubber is usually that's soft. So glass transition temperature is very low, but plastics is almost solid. So glass transition temperature is very high. Okay, so well, usually plastics is the materials. Well, also rubber is materials. Okay, so this is temperature dependence of the elastic modulus of plastics and rubbers. So this is typical plastics, polystyrene. Polystyrene are usually food containers. So glass transition temperature is 100 degrees here. Less than Tg, oh, yeah, almost at the room temperatures, almost a glassy state. This is almost that's a solid. And also polyethylene. Polyethylene is sometimes at a convenience store bag. Okay, so that's why glass transition temperature is very low, but at room temperatures, crystalline state. So almost at a, maybe solid, this one. So yeah, when we use these materials at room temperatures, almost solid, this one. Okay, but other one, that's the rubbers. So typical rubber, this is polybutadiene. So glass transition temperature is almost minus 100 degrees centigrade, this one. But room temperatures, elastic modulus, very, very low, less than 1 megapascal. Usually plastics is more than 1 gigapascal, or 1 gigapascal. So 3 or 4 there is different. So difference is very, very large, this one. But at room temperatures, rubbery state is almost a cross-linking or something. So maybe fluidity is not so large, so almost doesn't fluid. So rubber becomes the materials or become the tires, this one. But higher temperatures, maybe rubbery flows. And after that, viscous flow occurs, this one. So when we make rubber or plastics. So we use a viscous flow. After that, we make solid. So we use that maybe materials, okay? So what are organic materials? So organic molecules is molecules with a carbon atom backbone. Only carbon. Yeah, for example, graphene or carbon nanotube. These are not organic molecules. Organic molecules have another atoms. For example, hydrogen, oxygen, that nitrogen, this one. So in that case, we call that organic molecules. So some materials as plastics and also rubber, fiber, papers, gel, and biopolymers, and also the liquid crystal, the organic conductive material, some things. Almost material is polymers. Yeah, because polymers, at room temperatures, almost polymers, maybe solid. So we use that materials, okay? Yeah, but liquid crystal at room temperatures. So maybe lower molecular weight liquid crystal is not polymers. But almost as a liquid, okay? So covalent bond is maybe diverse molecules. So we connect carbon or hydrogen and oxygen and nitrogen and the other atoms. We make many kind of polymers, okay? So also that diverse molecules is. But at past, so that means human uses the natural rubbers, silk, cotton, wool. So establishment of polymer theories is almost 1930s. So almost 100 years ago. So maybe history is not so long, very short time, this one, okay? So 1935, nylon is established. So that one is the first synthetic rubber. So that's catchphrase. Fiber finer than the spider silk and stronger than steel. I like this catchphrase, this one. So in this case, that one is the beginning of the era of synthetic polymers. I like these pictures. This is Wolfram Carozas. So he also developed the synthetic rubbers. So so now that he had that rubber, this one, and elongated rubber, this one. Okay. So this is the characteristics of polymers. They're usually that's lightweight. So that means that small densities, because mainly composed of light elements such as carbon, hydrogen, oxygen, and nitrogen. Okay, and easy to mold, and soft, and viscoelasticities. Sometimes rubber, this one. So that one is a molecular, because molecular chain are easily bent, this one. And sometimes that's a very strong materials. Yeah, if we use the covalent bond, covalent bond is very, very strong bonding, this one. If we use that one, we make that very, very strong material, this one. And also easy to make fibers, because polymer is long molecule, this one. And also easy to decompose, and also biocompatibility. So because of these are organic materials, okay? So lastly, that I said it's a covalent bond is very important in these materials. So we make the diverse molecules. That means the diverse states also. In polymers, at amorphous phase, almost like this one. So we call that one the random coil, this amorphous state. But crystal state, molecules arrangement like this one. So maybe covalent bond is very, very strong. So, but that one is easy to rotate it. But these directions, very, very strong. But between the molecules, that's only weak interactions. That's a very, very weak, this one. So maybe this only these directions, that's very strong materials, but this directions, very, very weak materials, this one. So this one is the average to this one, okay? So anyway, we use the covalent bond. We make the very, very strong materials, this one. And also this is the size of polymers. So this is 1 meter, 1 millimeters. Sorry, this is 1 micrometers. And here is 100 nanometer, 10 nanometer, 1 nanometer is 1 angstrom. Yeah, our hair is almost 100 micrometers. Okay, and CC bond, this one is almost at 1.5 angstrom. This one, very, very short. This one. Yeah, this is the example of polymers. So that one is a polymethyl methacrylate. We call that one as acrylic resin, this one. So sometimes we use this molecules. So because molecular weight just 100. So yes, carbon is 1, 2, 3, 4, 5, and oxygen is 2, and H is 8. In this case, just 100 this one. So calculation is very easy one. So maybe this is a monomers. Monomer connected to 1,000. So 100 times 1,000 means that's 10.5. So that one is molecular weight. So degree of polymerizations, that means the number of monomers. In this case, 1,000. This one. The length of these molecules. So maybe here, CC bond is 1.54 angstrom. So maybe, okay. So total length is 3,080 angstrom, this one. But carbon has only 4 arms. So tetrahedral angle is almost 110 degrees. So we fix that angle. In this case, so longest structure is like this one. So we call that a flat zigzag extended chain. So in this case, this distance is only 2.5 angstroms. So maybe this length is 2005 angstrom, this one. Okay. So this is maybe chain length, this one. Okay. But in amorphous, so maybe that molecules become that random coil like this one. So this size is almost at 300 angstroms. We don't explain that in detail, this equation, but that just size is almost at 300 angstrom. Okay, 300 angstrom is here, so that one is 30 nanometers. But this one, that just length, that one is 250 nanometers. So still very, very small one. Anyway, yeah. Student, remember that this size, this one, that's very important things for this one. And also densities. Polymers density is almost around 1.0, this one. Maybe polyethylene. Polyethylene is a convenience store bag materials. That one is almost 0.85 or 0.9. That's a very maybe lightweight. Okay. But PTFE, polytetrafluoroethylene, this one is that now maybe many students know that the Teflon, that density is very high, that's a 2.2. But almost polymers around 1.0. Yeah, for example, polystyrene 1.04. So almost the same as water, this one. So anyway, you remember these things also, this one, okay? Now, yeah, we said that the polymeric materials are sometimes flexible and sometimes strong, this one. So that usually the covalent bonding is very strong, stronger than the melt bonding and ionic bonding, this one. Now, that this one's are amorphous structures, and this is the crystal structures. So maximize the covalent bonding, this one. So like this one, this is free extend chains. So free extended chain is very, very strong, this one. So we make this one by polyethylene or aramid fibers. Maybe somebody here that's a Kevlar one. So this one is a very, very rigid chains. So this material sometimes used for bread-proof vest like this one. So that's very, very strong. That's a fiber, this one. So that fiber is almost at a free extended chains. Okay. So next, that's some plastic and some setting polymers. So usually we use the thermoplastic polymers. So that's when like a chocolate is this one. So yes, let's make chocolate. That means that let's make that some plastic polymers. So at first, yeah, melt chocolate in a lot of the hot waters. Chocolate maybe may melt. So pour melted chocolate into mold. So cool and harden. So we get that, maybe materials. That means completed when removed from mold. So we get this one. For some plastic polymers, same things occur this one. Chocolate is almost a plastic materials. Mold with poured chocolate correspond to metal mold. So the mold with poured polymer, some plastic polymers correspond to the metal mold. So tool used to pour, maybe not chocolate, this is plastics is molding machine. Plastic product of various shape can be made from the various materials. Okay, but another polymer exists. So that one is a thermosetting polymer, this one. A little different from thermoplastic polymer, this one. So maybe thermosetting polymer correspond to the cookies, like a cookies. In cookie, so when we make cookies, that's a mix flour, butter, and other ingredient. So and shape materials, heating in oven. Finished cookies, we eat that one, okay? In the case of thermosetting polymers, mix starting materials, well, almost at a liquid this one, and plus hardeners and other raw materials. Sometimes they are poured into mold and shaped. After that, accelerate curing reaction by the heating. So various thermosetting polymer products can be made this one. So yeah, actually that's a processing route is like this one. So for thermoplastic polymers, usually that at first we use the polymer pellet. Polymer pellet is maybe 2 or 3 millimeter size, this one. Maybe everybody knows that thing. And the heating, that polymer melt. After that, we inject into the mold. So we remove the polymer from the mold. So we get materials. After that, remelt. So in that case, renewable, okay? So that's polymer is polymethyl methacrylate, acrylic resin, or polyethylene, polystyrene, polycarbonate, polypropylene. Polycarbonate is some window materials or carport roof or some things, and polypropylene. Polypropylene is maybe car bumpers materials. And polyester. Polyester is a polyethylene terephthalate, is a pet bottle or something. So. And also polylactic acid, and also nylon, etc. This one. And thermosetting polymers. So that's a processing route, this one. So raw materials, almost a liquid. So injection into that mold, almost same things. So this is in thermoplastic polymers. This melting is a very viscous melt. But in this case, this one is some very low viscous liquid, this one. So both one inject into the mold. But in that case, in that thermosetting polymers case, that's heating. So maybe materials become that almost solid or something. Oh, sorry. Then, we get that materials, but in that materials cannot be unrenewable. So in this case, in some plastic polymers, maybe everybody knows that epoxies and phenol resin and real resin, etc. Okay. So this one is a molecular interpretation of both thermoplastics and thermal setting polymers, this one. So, for example, thermoplastic polymers, higher temperature is almost at a melt. That means amorphous. So in this case, liquid. At cooling, so that materials become glass or crystal. So become almost as a solid, this one. After that, heating, they also remelt or something. So we can process repeatedly, okay? But some setting polymers, so involves the reaction during molding, this one. At first, that's monomers, before heating. So that's almost as a liquid one. After heating, maybe during heating, that the reaction starts. So cross-linking or chain extension reaction occurs. So materials make that three-dimensional network structure, this one. So that's why it's almost a solid, this one. So we cannot remold because with three-dimensional network here, this one. Okay. So this is a typical thermosetting resin. Thermosetting, that's polymers, that's epoxies. So this one is a typical epoxy resins that we call that bisphenol A type epoxy resins. So this is the most common that epoxy resin, this one. So this is the epoxy group, this one. Maybe ring structure here. So this one is an example of reaction between epoxy and amine. So this is NH2. This one react with the epoxy group, this one. So after that, chain extension exists, just become polymers. So epoxy is the main gradient, and amine is a curing agent. So in that case, that's why the two-component epoxy, this one. So before we use epoxy resins, so two component is mixed. After that, we mold that thing at higher temperatures. Okay, so maybe sometimes take 1 hour or something. After that, so maybe that one becomes solid. So after that, we use that materials. And also, second one is that amine cross-linking reaction, this one. First one is the chain extension reaction, but this one is a cross-linking reaction, this one. So that one make network, this one. Okay. So special characteristics of that epoxies, that's relatively that small volume shrinkage during curing compared to the other thermosetting resin, and high strength and heat resistance is very good. Dimensional stability is good. Also water resistance is good. Also chemical resistance is good. And excellent durability and electric insulation, low cost. So many things is very good, but not recycled, this one. So that's problem, this one, okay? And maybe after that, almost students make some soft robot. Maybe they use it as silicon rubber, this one. So I explain silicon rubber, this one. Silicon is a generic term for synthetic polymer compound with main backbone of siloxane bond. Siloxane bond is a SiO(Si), this one. So maybe room temperature vulcanized silicon rubbers, RTB silicon rubber, this one. Vulcanized means that almost cross-linking, okay? So room temperature cross-linking silicon rubbers, okay? That one, Cure also make cross-linking, this one. At room temperature and becomes the rubber elastic. So usually epoxy resins So cross-linking density is very high. So in that case, that materials become solid. But silicon rubber cases, maybe cross-linking is very low, this one. So that's not become that solid, still rubber, this one, okay? So RTB silicon rubber is a liquid or paste that's before curing. So RTB silicon rubber can be classified into two types, one component type and two component type, this one. One component type is curing reaction can be triggered by moisture in the air. So like this one. So, yeah, that's very easy, this one. Okay, but another one is a two component type. So curing reaction can be initiated immediately by adding a curing agent to the base compound. So one component and two component. After that, after reaction, that siloxane bond exists. Okay. So in this case, yeah, before using, we mixed both components. So and we mold that one, and we wait for, I don't know, for example, one day or something. So after that, we get some maybe sample or something, this one. Okay. Well, also that many types of maybe silicon rubber exist. Maybe, yeah, student use as a sealskin 10. Sealskin 10 is a two component type epoxy. Silicon rubber, this one. So maybe that reaction is like this one. Maybe one component, two component, we use the catalyst one. This is platinum, this one. So after that, we get this morphology, this one. Okay. So silicon rubber is very soft. So, but chemical resistance is very good, this one. So that's very nice materials. Maybe usually that I don't use that one, but we use that one as adhesives, this one. This one also adhesive, this one, okay? And various molding method for that some plastics one. So with some portion that's Japanese, so sorry, this one. So very popular, most popular that molding, it's injection molding, this one. So this is cylinders and this is mold. So melted polymers go to the mold. After cooling, we get the materials like this one, okay? So this one is a high productivity one. That's very nice. So usually that molding time is almost less than 1 minute. So this is most popular, this one, okay? Another molding, this one, that's extrusion molding, this one. So maybe when we use some PVC, polyvinyl chloride, so that's very difficult to process something. In that case, we use that extrusion molding, this one. So that one, yeah, we make the drain spout, water hose, and wire coating or wire coating, this one. And another one is maybe blow molding. So everybody uses the PET bottle, this one. PET bottle is made from that blow molding. So at first, we make Parison by extrusion molding, this one. After that, we blow airs, this one. So after that, we get the PET bottles. And also that's a car gasoline tanks from this method, this one. This is also maybe very popular, this one. And calendar moldings. So maybe, yeah, when we make that PVC sheet, so we use this method, this one. And also inflation molding. So, yeah, for example, convenience store bag or garbage bag or something. So maybe we get this one. So many kind of that molding method exist for the thermoplastics one. So now next, that's a bias molding, that's a method for thermosetting polymers. So molding process is using this low viscosity. So pour into mold or laminate. It does involve reaction during molding. So most popular one is a cast molding. So this is mold, and we pour the thermosetting polymers to this one. Okay. After that, maybe waiting or heating and waiting. So we get the materials. This one. Okay. This is very popular. And another one is that laminating or lay-up molding. This one. And also, almost same thing. This one's hand lay-up molding. This one. When we use bathtub or something, we use this one. Okay. And also compression molding, this one. So when we make the helmet, we make this method, this one. So anyway, so every student make soft robot. So in that case, maybe they use this silicone rubber as well. In that case, we use this one, cast molding, this one. Okay. And when I explained the plastics, so maybe automobile parts is very popular, this one, for maybe industry, this one. So automobile plastic parts, that's front bumpers, instrument panel, rear box decks and luggage trim and rear bumpers, many kind of that parts is made from plastics one. Biggest one is the front bumper, like this one. So, what function are required for bumpers? This one? And can we use rubbers? Or what kind of structures have to make it this one? So, what function are required? That means impact strength is very important thing. So. Okay, so maybe protect our body, this one. So maybe car or bumper is brake, but the human doesn't brake this one. Okay, so maybe car bumper is very important things, parts this one. So we make car bumpers by, injection molding. Sorry. Oh, sorry. So, sorry. So this is a sorry. Yeah. That's strange. Okay. Stay here. This is a not stay. Anyway, we use that also that injection molding for making bumpers. Okay. Let's show this one. And next, the tensile properties. So ductility and brittleness, this one. So everybody knows that maybe tensile testing, this one. So that's why the stress strain curve like this one. So here, so this is break at very low, very low strain, this one. So this point, the elongation at break, this one. Elongation at break is very, very small case. So that one we call it brittle. So some polymers that's very brittle one. So that one is a polystyrene, acrylic resin, cast iron, and concrete, this one. And another one is the ductile materials one. So in ductile materials, plastic deformation occurs. So in that case, like this one. So maybe we call this portion the necking. Neck is maybe here's neck, this one. After that, break. Okay. So in that case, elongation at break is larger one. But still, modulus is high. Okay. In that materials, that's a polycarbonate and stainless steel and dural means, okay? And another one is rubber. So rubber is maybe modulus is very, very low, but elongation break is very, very larger. Okay, so maybe usually that big three type materials exist. Okay, so and also some materials brittle ductile transition occurs. Maybe at room temperatures brittle. That's for example, PMMA is brittle at room temperatures, but 80 degrees or something. So that materials become ductile material, this one. So this SS curve, yeah, maybe has a temperature dependence, this one. So that means that maybe brittle ductile transition exists, this one. Okay, yeah, another the mechanical properties, important mechanical properties, impact testing. So that maybe low impact strength, that one's brittle also. So, and high impact strength, maybe sometimes ductile, this one. Yeah, okay. So in tensile test, that's a brittle ductile exists. Also impact test, that's a brittle ductile exists, this one, okay. And this one is characteristics of polymethyl methacrylate. So this is acrylic resins. So maybe monomer structure is like this one. So anyway, when we use materials, we know that advantage of disadvantage of that materials. That's very important thing, this one. So yeah, if we know that things, we can select suitable plastics, this one, okay? So maybe, yeah, I showed that some advantage of PMMA. So advantage is higher that light transmittance, transparencies than glasses, okay? And outstanding outdoor weather resistance, and elegant and beautiful lusters and design abilities. So that's very, very nice plastics one. But PMMA has some disadvantages, brittleness, and also water absorption. Okay, so applications. So many applications exist. That's the automobile, that's the tail lamp. Yeah, here is this one. At metal covers and household goods, nameplate for audio visual equipment. That's shop equipment. So and lighting. That covers one, the plumbing that handles and the various signboard displays, and also roof and other construction materials and aquariums. That's very peculiar, but it's very interesting, this one. This is the Churaumi aquarium in Okinawa, this one. So this is the biggest window of aquariums in Japan, this one. So that's what the PMMA is, not inorganic glass. This is just PMMA, that's a polymeric glass, this one. That's very interesting. So another one is a general purpose extrusion board, this one, carport roofs. And also this is a vending machine face plate, this one. That's an impact resistant that extrusion board. So many applications exist. Okay, so yeah, windows are also that's plastics one. So usually that's aircraft and aircraft windows that are usually that's 3-layer structures. So outside is PMMAs and inside is polycarbonate. Yeah, a little peculiar as well. Polycarbonate is polycarbonate is ductile materials and the PMMA is brittle materials. But outside is PMMA, inside is polycarbonates. So that's a little peculiar, this one. But outside of the PMMA windows, that's a very, very high molecular weight. If it's so, that one is maybe impact strength is very large, this one. So we use that PMMA, okay? And also, that's interesting, this one. This is the Japanese Shinkansen, this one. So this is the N700 series. This windows, every windows, polycarbonate is this one. Before N700, this windows, inorganic materials, that's just glass, this one. But from N700, this window is polycarbonate, just plastics one. That's very interesting. Okay. And also some cell phone that display Windows PMMA something. Now that's a iPhone or something, it's glass or inorganic glass, this one. And also, yes, ceramic aquarium, this is large scale aquarium, this one. And also that, yeah, this is good looking. So this windows, this is PMMA or polycarbonate, not inorganic glass. Inorganic glass is sometimes very dangerous. If it break, some small piece is scattered, this one. So, and that's very dangerous, this one. So, yeah, maybe fighting plane, windows, just plastics. That's very interesting. Yeah, this one is a Churaumi aquarium large tank, this one. So this is, yeah, I said that this is PMMA. Thickness is 60 centimeters. So this one, height is 8.2 meters, width is 22.5 meters. Almost one big plate, this one. So this windows, maybe Japanese very small company makes that one. So Nippura, that's the company name is Nipras. Yes. So this one is maybe shared #1 in all over the world for aquarium that windows, this one. Okay. So also this one, yeah. My daughter take these pictures. And also this one is Aquamarine Fukushima's large water tanks. I take picture this one. Also big one, this one. So here, human, this one, okay? After that, we go to the backyard of this aquarium, this one. So in this case, some window material there, this one. So maybe this one is a 6.5 plate of PMMA is 1, 2, 3, 4, 5. So total the thickness is 32.5 centimeters, this one. That's thickness, this one. So this is PMMA. So we adhesive 1 and 2 and 3 and 4 and 5 by PMMA, the monomers. PMMA monomers is MMA. So after that, MMA becomes that polymers. That means that adhesive, this one. So after that, this plate become only one. Okay, that's very interesting, this one. And the next is a polyethylene. So I said it's convenience store bag, this one. This is a very most simple structure of polymers. Just CH2 and CH2, this one. So this is chemical structures, but maybe long chain. So this is a little three-dimensional figures, this one. So that one is maybe CC bond can rotate easily. So that means very, very flexible. Okay. So that's flexible chains. So amorphous structure is this like this one. This is random coil, this one. But these materials make crystals. Crystal size like this one. This is maybe platelet, this one. So we call that one lamellas. So lamella is a plate that's crystal, this one. So this one, many that's lamellas like this one. So this is spherite. So this is crystal, this one. So this is aggregate of spherite. So this is yes, convenience store bags morphologies, this one. Okay. So anyway, that's long molecules polymer, this one. So, but this one is a polyethylene crystal. So this is single crystal, made from dilute solutions. So this structure is this one. So in crystal, so maybe polymer chains arrange regularly this one. So that's crystal, this one, okay? But in materials, so many spheroids exist, this one. In that case, yeah, lamellar structures like this one. So this is crystal lamellar, this is amorphous state, and also crystal. That's maybe crystal plate stacked. And maybe grow from center to radial direction, this one. So that makes it a spherical shape, this one, okay? So application of polyethylene, that's a plastic bags, beer bottle case, and rope and string. So many things, this one. So, あれちょっと早かったかな。So, yeah, up to now that my time is finished. Yeah, if a student has questions, please ask me this one.
Professor,
Hi, yeah,
I actually have one question.
yes.
So I'm not in the material field. I'm a theoretical researcher working on mathematics. So every time I'm an optimization researcher. So
yeah, not mechanical engineering or something, no?
Yes, like optimal design of mechanical components, something like that. So I'm not really familiar with the material science. So whenever I see a paper like with a slide or a figure like this,
Yes.
every time I see researchers try to draw how the how do I say particles or molecules, I don't know, I'm not sure what's the right word, the shape of the polymers, like a or maybe the crystal one.
A crystal one, yeah.
Yeah, so you draw something, people draw something like describe how they properly aligned in a directional way. How do you guys know they really looks like this? Is it based on imagination or?
No, not imagination as well.
Oh,
we measure this one. For example, yeah, we use X-ray or transmission electron microscope.
Yes.
So we check this morphologies.
I see.
Actually, this morphology exists.
I see. So I believe you have material science researchers have done a lot of testing, measurements, observation by really precise equipment.
Yes.
But because they're so small.
Yeah, so small.
So sometimes I have this question: How did you? What is the trick to realize? In fact, the material looks like this. That's only out of my curiosity. Because I have no experience. Maybe you can share something about how researcher define the shape of those geometry. Yes.
Okay. Yeah. Sometimes we use the transmission electron microscope. So resolution is almost at less than, almost at 1 angstrom. That means 4.1 nanometers. This one.
Okay. So very precise.
Yes, very precise.
I see.
Yes, I like that TEM. Also, maybe scanning electron microscope. So that's why the maybe resolution is maybe several nanometer or several 10 nanometers. This one. Also small one.
I see.
So
basically, after this precise observation, you just draw a nice sketch based on the observation.
Yes,
I see. Thank you.
So yeah,
that answers my long-term question in my mind. Thank you very much.
When we use TEM, some people make that some atoms.
Okay. Wow.
Atom is very, very small.
Yes. Yes. Wow.
Yes.
Okay. Thank you.
So,
Thank you for the
yeah,
question.
Some people arrange that atom this one by TM. This one.
I see. I see. Okay.
Yeah.
Professor Zhuang, I'll give the time back to the host.
Uh-huh.
Thank you very much.
Yes, thank you very much. This one.
Does anyone
Any
have
other
any
questions?
questions for Professor? Okay, let's see if we have any questions in the Zoom. It seems not.
No?
Well, students are shy, always shy. Okay.
Ah, okay.
Well, it's around 9:15 now in Taiwan time. So probably, can we take, homework? Oh, by the way, do we have a homework?
Homework, maybe Professor Kuboyama give us a homework, this one, later.
Okay, all right.
Okay. So maybe he starts from the 10 o'clock.
10 o'clock or
Okay.
10:05, yeah. How about that? We start the second lecture at 10:05. Is this good?
Right.
Yeah, 5 minutes after the 10 o'clock.
Professor Kuboyama, okay?
Okay.
Okay, okay, sounds good. All right, so let's take a time of a 10 minutes break.
Okay, thank you very much.
Thank you.
Bye-bye.
Bye-bye.